All right, let's go ahead and get started. We are well on our way towards understanding rice tables. You are going to need a calculator for this one, so if you don't have one handy, go ahead and pause the video and we'll get started. So here we go. Problem number 4 says this. It says the equilibrium constant Kc for the reaction is PCl, this is the reaction. PCl5 is a gas in equilibrium with PCl3 and Cl2, all are gases. And they tell us that that equilibrium constant is 33.3 at 760 degrees. Folks, the 760 degrees really is not of concern to us as long as we know that if we change that temperature, that the equilibrium constant is going to change. But it really doesn't enter into anything as far as we're concerned. Here's what it says. If 0.4 moles of PCl5 are placed in a 2-liter container, calculate the equilibrium concentrations of all species. So we are going to be looking then for the E line, right? We want to know what the equilibrium concentrations are given that the Kc is 33.3. How do we approach this problem? Well, obviously with a rice table. So the reaction again was PCl5 in equilibrium with PCl3 and Cl2. So that's the R part, or the reaction part of the rice table. Now, we are told that we've got 0.4 moles in a 2-liter container. I want concentration here, so I'll just do a quick division in my head. 0.4 divided by 2 is 0.2. So that's the initial concentration of the PCl5, but what about PCl3 and Cl2? Well, no mention is made of those, so we'll just assume that we're going to start with none, 0. No PCl3 and no Cl2. So that'll do it for the initial line, the initial concentration line. So what's happening? Well, in the change line, we know we're going to have to move towards where the zeros are. I know it seems like it's always going to the right, but believe me, there will be problems where we'll move to the left if the zeros are on that side. So we've got plus and plus on this side and negative sign on this side. Now this is a balanced reaction. It's 1 to 1 to 1. So it's just minus x on this side, plus x over here, and plus x over here. And that gives us the C line. To get the E line, we just add up the initial plus the change. 0.2 minus x is 0.2 minus x, 0 plus x, 0 plus x is x. And we now have our rice table and we're ready to write our equilibrium expression. So let's do that. So Kc then is equal to products over reactants. All these are coefficients of 1. So I'll just go ahead and put a 1 here, a 1 here, and a 1 here. Not that it really matters, but that's the equilibrium expressions. Products over reactants. So we've got concentration of PCl3 times the concentration of Cl2 over concentration of PCl5, just like that. And we have been told that the Kc for this expression is 33.3. So let me plug that in. So from the line, from the equilibrium line, I know that the concentrations of the PCl3 and the Cl2 are both x, right? They're both x. So I'll just say x times x, x squared. Over PCl5's concentration is 0.2 minus x. That'll go on the bottom. Now we're going to do a little bit of algebra now. We're going to pull that 0.2 minus x up to the top, multiplying it by the 33.3. And here's what I get. 6.66 minus 33.3x is equal to x squared. Now I'm just going to pull everything over to the right-hand side. I like to have the first number as positive. So I'll just pull everything over and I get this. I get 0 is equal to x squared plus 33x minus 6.66. Now let's just pause a little bit and talk a little bit about where we're going to proceed from here. From this point forward, what are we going to do? Well, that's obviously a quadratic equation, right? That's obviously a quadratic equation. So to solve this equation, I'm going to need the quadratic equation, right? So I'm going to go ahead and solve it using the quadratic equation, but I'm going to show you an easier technique that's going to allow you to get the answers much more quickly. So here we go. The quadratic equation is this. It's x equal minus b plus or minus the square root of b squared minus 4ac over 2a. So you know that from your algebra class. And so when I plug these numbers in, I end up with these values, negative 33.5 or positive 1.99. Now, only one of those two answers is correct, right? Only one of those two answers is possible. So here's what I want to tell you. If you get one number, if one of the two numbers that you get is negative, right? I'm going to pull this down just a bit because I want to show you something here. If one of those two numbers is negative, just throw it out. It's not the answer, okay? So it can't be a negative. You can't have a negative concentration. Now, it is possible that both of the numbers are positive. It can happen. But if both the numbers are positive, then one of them will simply not make sense. So for example, let's just say that instead of getting negative 33.5, I got 0.199, and then I got 10 for the other one. Okay, I got 10 for this one. It's a positive number, but it won't work because look what happens when I plug this in. 0.2 minus 10, that's going to be a negative concentration for this right here, the PCl5. Can't have a negative concentration, so that won't work. So either one of them will be negative, in which case you'll throw it out, or the other one, or one of them just won't make sense. Okay, so you'll know to throw that one out as well. So this is our answer right here, 0.199 is X, right? Now, we're not done yet because we're going to need to actually formally report what our concentrations are. So we know that if X is equal to 0.199, that means the equilibrium concentration of PCl3 is 0.199, and so is the concentration of Cl2. So I'll report it just like that. And to determine the PCl5 concentration at equilibrium, let's go back up to the Rice table. We have 0.2 minus 0.199, and we get for that concentration 0.00100 moles per liter, and that'll do it for that problem. Before we go on, though, I do want to tell you that I use the quadratic formula or the quadratic equation to solve for this X. It can be quite tedious if you do that. I would make a recommendation that you do this. There is a program that you can plug into your calculator. If you've got a TI 83 or a TI 84 like I have, called QuadForm. Okay, QuadForm. Just do an internet search on QuadForm or do a YouTube search on QuadForm. This program is extremely easy, and you might just want to plug that one in and just have that app ready to go, because the fact that you just don't have time. You will not have time to be plugging into a quadratic equation. So QuadForm is what I recommend. If you've got a TI-89, it's already pre-programmed in the calculator for you. But if you're using an 83 or 84 like I am, then you're going to need to program it in. So that's it. That's it for rice tables, and we want to move on now. So let's go. Folks, what we want to talk about is something called Lachat principle. All right? What do we mean by Lachat principle, and what does it say? Well, we've talked a lot about equilibrium, right? And what we said was that equilibrium was what happens when the forward and the reverse reaction rates are the same, right? So if we had this equilibrium, we have a squared, which is a gas, plus b squared, which is a gas, in equilibrium with 2ab, which is a gas, right? Lachat's principle says that if you stress the system, and we'll talk a little bit about what that means, that the system is going to react in such a way to reestablish equilibrium. So if you disturb or perturb the equilibrium, Lachat's principle says the system will react. It will react in such a way as to reestablish equilibrium. Well, how can we, what does that mean to stress the system or to perturb the system? Well, there are a couple of different ways that we can do that. One way is by affecting concentration, right? So let's talk a little bit about what happens if I change the concentration of something. So let's just say, for example, that I were to add B2 to the equilibrium. So I've got the equilibrium going, but then I add B2 to the equilibrium. What's going to happen? Well, if I add B2 to the equilibrium, what's going to happen is the equilibrium is going to be disturbed in such a way that it has more B2 than it wants. So if I add, say, B2, if I did that, what's going to happen is that the system is going to shift to the right. That at least momentarily, if we said that this is R1 and this is R2, remember, before the stress, R1 and R2 were the same. But at least initially, when I add that BR2 or that B2, what's going to happen is that the reaction rate to the right is going to exceed the reaction rate to the left. And it's going to do that until it reestablishes the equilibrium that was previously there, right? It's going to continue to move to the right faster than it is to the left. In other words, R1 would be greater than R2 as a response to this perturbation of the equilibrium, right? Now, I've talked about what happens when I add B2. What if I take something away? What if I say, for example, were to remove A2, right? So somehow I could get A2 to leave, right? And by the way, this is an effective system in different chemical processes. One is called the Haber process, and I'll talk about that a little bit later. But for right now, I want to know what happens if I get A2 out of the system. I create a stress in the system. Well, what's going to happen is that the system is going to respond. If I take A2 out of the system is going to shift this way towards the A2 to try and create more of the A2, right? I've taken it out of the system's going to respond to try to counteract what I've done. And so now what's going to happen is that as a result, R2 would be greater, the rate in the reverse reaction would be greater than R1, just like that. So that's one type of stress on the system. What's another type of stress? Well, another type of stress is a reaction to volume or pressure. And these two are absolutely related. We know that from our gas law experience in a previous unit. Here we've got PCl5 in equilibrium with PCl3 and Cl2. Now, if I were to ask you which is the high pressure side of this system, you would say, well, I've got, let's see, 1 mole here, 1 mole here, and 1 mole there. So I've got 2 moles of gas on the right-hand side, and I've got 1 mole of gas on the left-hand side. So the high pressure side would be on the right-hand side of the equation. So what happens if I increase the pressure of the system? What happens if I increase the pressure of the system? Then what's going to happen is the system is going to shift, according to Lachat Liaised principle, away from the high pressure part of the equation. It's going to shift to the left. If I were to increase the volume, right? Increasing the volume is the same essentially as decreasing the pressure. So if I decrease the pressure, it's going to shift toward the higher side, higher pressure side. It's going to shift that way. So I can either increase the volume of pressure or decrease the volume of pressure, and that's going to elicit a response via Lachat Liaised principle to the left or to the right. Okay? All right. And the last type of stress that we want to talk about is we want to talk about, let me go on, temperature. All right? We want to talk about temperature. All right. So let's just say, for example, that I were to tell you that this was an endothermic process. An endothermic process. That means in the production of NO2 from N2O4 that it requires heat. So heat's on the left-hand side. Well, what happens if I heat up the system? If I were to heat up the system, I would accumulate too much heat and the system would shift to the right. On the other hand, if I were to cool down the system would attempt to replace the heat and it would shift it to the left. So that's it. That's really the Lachat Liaised principle. There's 3 stresses that we want to think about. The first one is, we talked about the first stressor. We talked about was, let me get back there. We talked about, well, even a little bit more. Here we go. The first stressor that we talked about was concentration, and we know the effects of concentration, increasing or taking away concentration. The next one was volume or pressure, and the last one, of course, was temperature. And we know that temperature had to do with whether something was exothermic or endothermic. Folks, that'll do it for this one. I'll see you in the next one. Thanks. Bye.